Okay, let's go through this question together. This is going to be 1.6 momentum, yeah? Looking at the question here, an air piston fires a pellet forward. What is the motion of the air piston here? Now, this here is exactly what's going to happen in an explosive collision. When you pull the trigger in the gun, what's going to happen is the bullet is actually going to fly forward and the gun is going to fly backwards here. Now, I know for a fact that the speed of the bullet is definitely going to be much faster simply because it has less mass, whereas the speed of the gun is going to be much slower simply because it has more mass. So looking at the answers here, the air pistons move backwards with a greater speed than the pellet. This is definitely not true unless you're trying to shoot the gun instead of the bullet. The air piston moves backward with a speed less than the pellet. This is possible. The air piston moves forward with a greater speed than the pellet. Not possible. Air piston moves forward is not possible as well. So B is naturally the answer for this question here. Figure 2.1 shows an athlete crossing the finishing line in a race. As she crosses the finishing line, her speed is 10 meters per second. She slows down her speed to a speed of 4 meters per second. So this is the initial velocity and this is the final velocity here. The mass of the athlete is 71 kg. Calculate the impulse applied to her as she slows down. Now you guys have to remember, impulse, there is always two formulas. It's either going to be force times time, or it's going to be the change of momentum here. Now looking at these parameters here, obviously we do not have force nor do we have time, so we cannot use this formula and we must use this formula instead. From here, once you identified the formula used, all you need to do is substitute all the information in. It will be 71 multiplied by 4 minus 71 multiplied by 10 here. So if you press that in the calculator, 71 multiplied by 4 minus 710 here. What you're going to end up with is we're going to end up with negative 426 kg meters per second. But of course, you'll never write this negative here because impulse is the change of momentum, right? Doesn't matter if it's 0 changing to 100 or 100 changing into 0. The change will still be 426 in this scenario, kg meters per second here. Then after that, they ask you to define impulse in terms of forces and time. Since we know that formula for impulse is force times time, then we can say that impulse is the product of force and time. Okay, then you're going to get your full marks here. Then after that, moving on, the athlete takes 1.2 seconds to slow down from a speed of blah 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 to blah blah blah. Calculate the average resultant force applied to the athlete. Now if you guys recall, I mentioned that impulse, there's two formulas. It's either Ft or it's going to be mv minus mu. Since both of them are impulse, I'm just going to equate them both together. And if they're asking me to find force, F will be essentially mv minus mu over t here. Now since we already calculated mv minus mu as 426, I'm just going to write 426 divided by the total time of 1.2 seconds. Press that into my calculator once again, and I'll get a final force of 355 newtons here. So you're supposed to write this down here, 355 newtons. And finally, the force required to give a mass of 71 kg and acceleration of 6.4 here. This is mass, this is acceleration. They're looking for force, so it can be no other than F equals to ma. And at the end of the day, you'll get 71 multiplied by 6.4. Press that into the calculator again. You're going to end up with 454.4 newtons, but you can only write all your answers in 3 significant figures in this dotted line here, so you'll end up with 454 newtons here instead. All right, moving on to the next set of questions here. This is going to be the May June 2016 one. An object of mass 50 kg, this is the mass, accelerates from a velocity of initial velocity, final velocity in the same direction. What is the impulse provided to cause this acceleration? Yet again, impulse is basically mv minus mu, right? mv minus mu. In this case here, it will be 50 multiplied by 10 minus 50 multiplied by 2 here. So if you press this in the calculator, it's essentially going to be 500 minus 100 here, right? So it's going to be 400 Newton seconds. Why is it in Newton seconds? Because this one here is the second formula, which is force times time, Newton second here. All right. Then the second question, a gas molecule strikes the wall of the container. The molecule rebounds with the same speed. Keyword here is same speed. What happens to the kinetic energy and what happens to the momentum of the molecule here? Now, since the gas molecule is rebounding at the exact same speed, and since kinetic energy depends on speed, I can say that kinetic energy is definitely going to stay the same. However, momentum is going to change because momentum is a vector quantity. Towards the right is positive momentum, towards the left is negative momentum, and thus momentum is definitely going to change. Then, looking at this next part here, figure 2.1 shows a dummy of mass 70 kg used in a car in a crash test to investigate the safety of the new car. The car approaches a solid barrier at 20 meters per second. This is its initial velocity. It crashes into the barrier and stops suddenly. This is the final velocity. Calculate the momentum of the dummy immediately before the crash. Now, momentum's formula is basically going to be mass multiplied by velocity. In this case here, it's going to be 70 kg multiplied by 20, which is going to end up with 1,400 kg meters per second. 1,400 kg meters per second here. Determine the impulse that must be applied to the dummy to bring it to rest. Now, impulse is basically the change of momentum, right? And since it changes to stop immediately, and you can see that it's only one mark here, it's essentially going to be mv minus mu, which is going to be 1,400 minus 0, which will still give you the exact same answer as you got previously. That is why it is only one mark. Whenever you see it's one mark questions, you can consider it as conceptual question. So you have to be very careful when dealing with these kind of questions. And finally, in the crash test, the passenger compartment comes to rest in 0.2 seconds. Calculate the deceleration of the passenger. This one here is just an application of formula. Acceleration is v minus u over t. Deceleration is exact opposite. It's u minus v over t here. So initial velocity was 20. It came to a sudden stop minus 0, divide by 0.2. Press that into your calculator and you'll get 100, right? Yep. You'll get 100 meters per second square. 100 meters per second square. Alright. Then, moving on to this next part here. Figure 2.1 shows two railway trucks on a track. The truck A is 6,000 kg moving at 5 meters per second. It is approaching truck B of mass 5,000 kg, which is stationary. So the initial velocity is 0. The initial velocity of A is 5, and this is mass 1. This is going to be mass 2. M1 U1 plus M2 U2. Calculate the momentum of truck A. Yet again, momentum is mass times velocity, which in this case here will be 5,000 multiplied by, oh oops, not 5,000, it's 6,000 multiplied by 5, because this is A and this is A, right? So you're supposed to end up with 30,000 kg meters per second. Write it exactly here, 30,000 kg meters per second as well. Right. And after that, the truck collides, their buffer compresses, and they bounce off each other. This one here indicates that they are elastic collision, remaining undamaged. After the collision, truck B has a momentum of 27,000 kg meters per second. This is truck B, meaning to say this is essentially M2V2, right? Because it's after the collision, right? Then determine the impulse applied to truck B. Impulse is yet again change in momentum, mv minus mu. In this case here, it will be 27,000 multiplied by 0 because initially truck B was not moving. So from here, you get a free marks of 27,000 kg meters per second again, right? And finally, they ask you, well, not finally, second last question, they ask you to calculate the average force on B given that this is the time. Yet again, you should recall that F is equals to mv minus mu over T here. In this case, it will be 27,000 divided by 0.6. Press that into the calculator. You're going to end up with a force of 45,000 newtons here. You're going to get 45,000 newtons here. Straightforward. And finally, they ask you to calculate the final speed of truck A here. I want to find out what's the final velocity of A, given that the final momentum of B was 27,000. Now this question here, if you're asked in IGCSE, most likely they're trying to test you on the principle of conservation of momentum. Principle of conservation of momentum states that the total momentum before collision is equals to the total momentum after collision here, which gives rise to the formula m1u1 plus m2u2 is equals to m1v1 plus m2v2 here, right? So once you identified this equation to be used, all you need to do is start substituting all the numbers in. m1u1, what you calculated just now, is supposed to be 30,000. Okay, so I'm just going to write 30,000 here, right? Plus with initial velocity, initial momentum of B, which was stationary, so it's definitely going to be 0, right? Is equals to the final momentum of 1. I don't know how much is the final momentum, but I know that the mass of A started off with 6,000 kg, right? It was 6,000 kg. Multiplied by V1, because V1 is the one that I'm looking for, right? Then after that, plus with the final momentum of B, which was said to be 27,000 here. It's going to be 27,000 here. So once you have all this equation, it's just a matter of algebra, right? You move this over, it becomes 30,000 minus 27,000, which is going to be 3,000, is equals to 6,000 V1, right? So ultimately, V1 will be just 3,000 divided by 6, which is going to be 0.5 meters per second. You're supposed to end up with 0.5 meters per second here, right? Oh, there's more. Oh, so much more. Okay, then moving on to this next question here. Figure 2.1 shows two cars A and B before they collide. Car B has a mass of 1,200 kg. Car A has a mass of 2,000 kg. Traveling towards B at 18 meters per second. So this is your U1, this is your M1, this is your M2. Calculate the momentum of A. Very straightforward. Momentum is yet again mass times velocity. In this case here, it will be 2,000 multiplied by 18, which is supposed to give you 36,000 kg meters per second. 36,000 kg meters per second here. Right. Then after that, the car collides and B experiences an impulse. Car A continues to move in the same direction with a momentum of 21,000 kg meters per second. This here, right, is basically the momentum after collision, right, which is essentially your m1v1. Calculate the momentum of B immediately after collision. Now from here, yet again, it is the principle of conservation of momentum, which states that total momentum before collision is equals to total momentum after collision here, which will give rise to the formula m1u1 plus m2u2 is equals to m1v1 plus with m2v2 here. So yet again, substitute everything in now. This is your initial momentum, right, which is 36,000 plus with initial momentum of stationary car B, 0, right, is equals to the final momentum of A, which they said to be 21,000 here, plus with the final momentum of B. I don't know what's B, but I know that the mass is going to be 1,200. The V2 is basically what I'm looking for, right? Because they want me to calculate. Oh no, they asked me to calculate the momentum of B2, of B. So I can just find this part here. This whole part is good, is what I'm looking for, right? So it's just a matter of algebra yet again. Is 36,000 minus 21,000 here, which is essentially going to give you x is equals to 36 minus 21, which is going to be 15,000 at the end of the day. 15,000 kgs meters per second. Very straightforward. Then after that, they ask you to determine the average impulse experienced by car B during the collision. Collision impulse is yet again change in momentum, and if the final momentum is 15,000 and the initial momentum is 0, the final answer will be yet again 15,000 kgs meters per second, because change in momentum is going to be impulse, mv minus mu, right? And finally, not finally, the car was in contact for 0.2 seconds. Calculate average force experienced by B during the collision. Yet again is F equals to mv minus mu over t. Change in momentum was 15,000. T was 0.2. So I think it's going to be 6,000, right? 60,000. Oh, no. 75,000. It's going to be 75,000 newtons here. 75,000 newtons here. A modern car is designed so that during a collision, the front section of the car is crushed and the contact time increases. The time is going to be increased. All right. Explain the benefit of increasing the time of contact for the people in the car. Now this question here is basically testing your understanding on the F equals to mv minus mu over t. When I say that the contact time increases, right, you're supposed to understand that the impact force on the driver or the passenger or whoever is basically going to decrease, right? Because force and time are inversely proportional, right? Explain the benefits of increasing the time here. You're supposed to mention as the time of impact increases, the force produced on the passengers of the car decreases, and thus creates less damage, produces something like that. As time of impact decreases, the force produced on the passenger on the car decreases, and thus produces less force during a collision and sustaining less injuries. Okay. This is the final one. Yep. Final exercise here for momentum. Let's go. An object of mass 1.2 kg is moving velocity 2 meters per second. This is going to be the mass, this is going to be the velocity. When it is acted by a force of 4 newtons, the velocity of the object increases to 5 meters per second. Sorry, this will be u, this will be v. For what period of time does the force act on the object? So look at the parameters here. I have F, I have M, I have V, I have U. I'm looking for T, right? It can be no other formula than the F equals to mv minus mu over T formula. T will be essentially mv minus mu over F, which in this case here will be 1.2 multiplied by 5 minus 1.2 multiplied by 2 over F, which was 4 here. Press that in the calculator. 1.2 1.2 multiplied by 5 minus 1.2 multiplied by 2, then you divide it with 4. Press that in the calculator, you'll get an answer of 0.9 seconds, guys. You're supposed to get 0.9 seconds here. An object is moving at 3 meters per second. A force acts on the object. After a time, the object is moving at negative 4 meters per second. Now, this question here, I do want to highlight that because momentum is a vector quantity, if they say that this is a positive velocity, right, I can assume it's going towards the right. And if they say that this is negative velocity, I can assume it is going towards the left. The mass of the object is 5 kg here. So this is initial, this is final. What is the change of momentum of the body here? You should understand that change in momentum is essentially mv minus mu. In this case here, it will be 5 minus negative 4 minus with 5 multiplied by positive 3 here. So you'll end up with negative 20 minus 15. And at the end of the day, you're going to get negative 35 kg meters per second. All right, you're supposed to get negative 35 kg meters per second here. Then, next part. A ball falls vertically to the floor and rebounds vertically upwards. Before it hits the floor, its speed is blah, blah, blah. So this is your initial velocity. As it rebounds, the speed is blah, blah, blah. The mass of the ball is 0.5 kg. What is the change of momentum of the ball? Yet again, you have to understand that this here is a vector question because the ball is going to hit the ground and then it's going to rebound upwards, right? You can see that these two are different directions, so it should have different velocities. If I associate this as positive, this must be negative, guys, right? So pressing that into the calculator and writing everything in the formula will be something like mv minus mu, which is going to be 0.5 multiplied by negative 3 minus with 0.5 multiplied by 4, right? So you're going to get like negative 1.5 minus 2 here, which is going to give you negative 3.5. Now, because it is negative 3.5, right, I said going downwards is positive, then going upwards is negative, right? If I have negative here, it means to say it's going upwards as well. It is going upwards here, so it's 3.5 upwards. 3.5 upwards here. Then, moving on to the final parts here. An aeroplane has a mass of 2.5 times 10 to the power of 5 kg, lands with a speed of 63 meters per second on a horizontal run at a time equal to 0. The airplane decelerates uniformly as it travels along the runway in a straight line until it reaches a speed of 6 meters per second at a total time of 35 seconds. Calculate the momentum of the aeroplane when its speed is 6 meters per second. Very straightforward. Momentum is equal to mass times velocity, which is 2.5 times 10 to the power 5 multiplied by 6. Yeah, I think I'll need a calculator for this. 2.5 minus 10 to the power 5 multiplied by 6. You'll get exactly 1.5 times 10 to the power of 6 kg meters per second here. Make sure you always write your units. Then after that, next question here. Figure 2.1 shows a train. The total mass of the train and its passenger is 7,500,000 kg. Okay. The train is traveling at a speed of blah blah blah, its initial velocity. The driver applies the brakes and the train takes 80 seconds to slow down to a speed of 42 meters per second, final velocity here. Calculate the impulse. Impulse yet again, change in momentum law, right? mv minus mu, 3 marks some more, is basically 75,000 multiplied by 42 minus with 75,000 multiply by 84. Right. Press that in the calculator. You'll get a damn big number, which is essentially 3.15 times 10 to the power of 1, 2, 3, 4, 5, 6, 7 times 10 to the power of 7 kg meters per second. 3.15 times 10 to the power of 7 kg meters per second. Okay. And finally, calculate the average force applied to the train as it slows down. F is basically mv minus mu over t, right, at this point, which is 3.15 times 10 to the power of 7 divided by the total time, which was 80 seconds here. Press that in my calculator again. It will give me a very weird number of 3.93. Oh, 94. 3.94 times 10 to the power of 1, 2, 3, 4, 5 times 10 to the power of 5 newtons. 3.94 times 10 to the power of 5 newtons. And that concludes the exercise for momentum.